Okay, hi everyone. My name is Mathieu Reymond, and today I will talk to you about a multi-objective reinforcement algorithm that we've developed that is able to cope with known nonlinear utility functions. Okay, so in multi-objective optimization, we have different objectives. They can be conflicting with each other, which means we have to make compromises. And here is a simple two-objective problem where we have three different compromises, 0, 10, 5, 5, and 10, 0. Now, depending on the decision maker, one compromise is better than the others. And we assume that this preference the decision maker has can be put into a function, a preference function, which we call the utility function. This function will provide a score for each compromise so that we can rank each compromise and pick the best one. For example, here is a utility function which takes the minimum value between R0 and R1. In this case, the best compromise is 5, 5, as its minimum value is 5, while the other ones have a utility of 0. Okay, so how does this go with reinforcement learning? Well, in multi-objective reinforcement learning, we have a sum of rewards, in this case vectorial rewards, since we have multiple reward signals, which means we have a vectorial return. This corresponds to one of our compromises on which we can apply the utility function on, which result in a scalar, a utility, a score on which we can maximize on. So basically we can apply the utility on the episodic return in order to get single scalar as a score. Now, if the utility is nonlinear, we can not apply the utility function on the individual rewards. So this would be very tempting to do. You just apply the utility function on every RT here, which means that every time step you get a scalar, you can use a single objective algorithm, and basically you're done. But this will result in a very different utility than applying utility on the whole episodic vectorial return. So the sum of individual utilities is not equal to the utility of the sum of rewards. Here is a very simple example to showcase this. Using the same utility function, minimum of R0, R1, you have this two-step DP, where at the first time step you get 0, 5, at the second time step you get 5, 0. And so the vectorial return at the end of the episode is 5, 5. If you apply the utility function at the very end, you get the utility of 5. However, if you apply the utility on every individual reward, well, you take the minimum of 0, 5, you get 0. Similarly here, you get also 0, so you get a utility of 0 instead of a utility of 5. Okay, so our algorithm will be able to cope with nonlinear utility functions, as we'll see later. What else is important to mention about this utility function is that it has an impact on the optimal policy. So in reinforcement learning, you want the policy that maximizes the expected discounted sum of rewards. But here you get vectorial rewards. So you have two possibilities here. Either you apply the utility on the expectation of the rewards. So you apply the utility after the expectation. We call this setting scalarized expected return, SER, since the scalarization happens after the expectation. And in this setting, well, you learn a different optimal policy than if you apply the utility function directly on the sum of rewards. So this is the other possibility. You apply u on the return and then you take the expectation. And that's what you want to optimize. This setting is called ESR, expected scalarized return, since you take the expectation on the scalarization. This is the setting we are interested in. So basically, we want a policy for which the utility is applied at the end of every episode. So every episode is important, so to say. We'll see that with a simple example that this leads to different optimal policies. For example, here is a one-step MDP. You have two possible actions. Either you take A1, which will always result in 3-3, or you take action 2, which results in either 0-10 or 10-0, with a 50% chance for each. Now, if you take the same utility function, depending on the setting, the optimal policy will be different. So let's look at ASR first. We apply the utility at the end of our episode. If we take A1, the utility will be 3, since we get a reward 3-3. Now, if we take A2, we either have 0-10, which means we have a utility of 0, or we have 10-0, which means we also have a utility of 0. So A2 will always result in a utility of 0. So under ESR, the optimal action to take is action A1. It has the highest utility. However, if you look at the other scenario, SER, you take the scalarization after the expectation, well then A2 has the highest utility, since the expected return for A2 is 5-5. You have either 0-10 or 10-0. In expectation you have 5-5. The utility is 5, which is higher than 3. So under SER, A2 is the optimal action. Okay, so you see this will lead to different policies. We are interested in ESR, the one where the utility is applied on each and every episode. How does this work with our algorithm? Well, we're proposing here multi-objective categorical actor-critic, which can cope with nonlinear utility function under the ESR setting. And in order to do that, we're going to take care of two things. First is that the utility function needs to be applied on the whole episodic return. For that, we cannot simply look at the future rewards. We are also going to keep track of the past rewards. So at time step t, you can estimate the future rewards you will get from t until the end of the episode. But you know the rewards you got from 0 until t. So we call this the accrued rewards. And knowing the accrued rewards and the future rewards, you can compute the episodic reward, since it's simply the past and the future summed together. How does this work concretely in our algorithm? Well, we're going to start from the single objective actor loss from a typical actor-critic algorithm. What basically happens here is that you compare what you actually encountered, the reward you encountered, with the reward that you expected. So you compare what you encountered with what was expected. If what you encountered is higher than what you expected, then you will increase the probability of taking that action. If it was lower, then you will decrease that probability. Okay. However, this only looks at future rewards. So our actor loss, well, is based on the same idea, meaning we are going to compare what we encountered versus what was expected, but we are going to add the accrued rewards so that we get episodic rewards here, on which we can then apply a nonlinear utility function. So basically what we're doing is we're looking at the encountered utility versus the expected utility, the utility we expect it to have, and if we have a higher utility, then we will increase the probability of taking that action. So that's the first element we use to cope with our setting. However, there is still a problem here, and that is that we're using our critic v values in our utility function. So the v value is an estimate of the expected return, but we don't want to apply the utility on expected returns. That's the other setting. We are interested in the utility on every single episodic return, not on the expectations. We have seen that this leads to vastly different policies, so we cannot just mix the two together. In order to cope with this, we're going to forego the classic critic that is typically used in actor-critic schemes, and we are going to go with a distributional critic. We are going to try to learn the whole distribution of future returns instead of simply the expected return. So we are going to learn, this is going to be our critic. The job of our critic is going to be to learn a multivariate distribution. In this example, it's a bivariate distribution because there are two objectives, where we do a categorical distribution in order to make it computationally efficient. Each bin represents every single possible vectorial return you can get, and the height of the bin represents the probability of receiving that return. So that's what our critic will learn. It will learn a full multivariate distribution of the future returns, and we are going to use this distribution in our actor loss. So instead of using the v values as before, well, we're going to use the accrued reward plus every single bin here. So we're going to basically apply every single possible episodic return you can get from the current states, and multiply that, with the probability of actually getting that episodic return. So that is in a nutshell our algorithm. We're going to see that it is actually necessary to have a distributional critic. So we did an ablation study where we used, where we have one version with and one version without the distributional critic, which I will show you now. We did this on a very simple environment where we have two corridors. Action A0 will lead to the first corridor, which will always result in, at the end, a reward of 3-3. Action A1 will lead to the second corridor, which will result in either 0-10 with a 50% chance or 10-0 with a 50% chance. So here are some results. We have our algorithm in red. Green is the ablated version with a simple critic, not a distributional critic. And we also used a third baseline in blue, which is a multi-objective extension of reinforce. What we basically did is use reinforce with accrued rewards so that we get episodic returns, so that we can apply the utility function on the policy gradient loss of reinforce. Reinforce doesn't have a critic, so it doesn't need to consider using a distributional or non-distributional critic. It will just optimize directly on the policy. And we see that well, our algorithm learns the optimal policy. It will learn to always pick action A0, which leads to the reward tree, while the one without distributional critic will learn the wrong optimal policy, the one that leads to A1, since its critic will learn that the expected return here is 5-5, which in turn will influence the actor to always choose action A1. So we see that the distributional critic is important. Next, we did some more experiments on two different benchmarks. The first one is Deep Sea Treasure, classic multi-objective benchmark with a limited number of states, where you have a submarine that is in search of a treasure. Every treasure has a specific value. Sorry. The further away the treasure, the higher the value, but at every time step you consume fuel. So you need to consume more fuel in order to get better treasure. It's the compromise to be made here. We did the first experiment with a linear utility function, a weighted sum. Basically, you say, well, it's 0.1 times R0 plus 0.9 times R1. You have a linear utility function, which means you can apply this function at every time step on the individual rewards, so you can use a single objective algorithm. We used as a single objective baseline A2C. We have two variants of A2C. The one where the reward is scalarized at every time step. We call this A2C time step in green. And we also have one in gray, which is barely visible here since it's hidden behind the red curve, where the reward is accumulated until the end of the episode, and only then is the utility applied. This way, a single objective algorithm can use nonlinear utility functions, since the only time the utility function is applied is at the very end of the episode on the full episodic return, since you accumulate the return over the whole episode. The downside is that you only get one reward signal at the very end of the episode, so you have very sparse reward signals, which leads to their own problems. Our algorithm, on the other hand, in red, receives rewards at every time step and is able to make good use of these rewards. So we see that even though we have a linear utility function, our algorithm is able to learn the optimal policy in red, while more reinforced, the reinforced baseline in this case is not able to learn it. In this case, it's because reinforce is stuck reaching the first treasure. The single objective baselines are able also to learn to converge to optimal behavior. This is to be expected, especially since the utility matches with the correct utility, and you can apply it at every time step. Nonetheless, our algorithm converges the fastest. The second experiment we're doing is with a nonlinear utility function, and here the story is different. So we imagine a scenario where you have a crew in debt that is trying to find a treasure before a deadline in order to take care of their debts. If the debts are not taken care of, you get a penalty if you get too late. This is all included in this utility function. The first part is basically a soft plus, where every reward below the depth is 0. Then it's just the identity function. Then you have the fuel that you need to take into account, and you have a penalty if you're late, basically. Okay, so this is a nonlinear utility function. The first thing to note is we're using the same baseline, is that the time step single objective algorithm, the one where the utility is applied at every time step, fails miserably. This is logical because the sum of utilities is not equal to the utility of the sum of rewards, so it's not learning the correct thing. However, the other ones are. So A2C terminal receives the correct utility at the end of the episode, but it's a very sparse signal, which means it has a very erratic behavior. So it's learning, but it's not convergent. It collapses quite often, while on the other hand, our algorithm converges very quickly to the optimal policy, and more reinforce, in this case, also converges to the optimal policy. Another experiment we then did is on a high-dimensional environment, which is called minecarts. You have a mine. You have a set of mines that have different ores, and the goal of the agent is to go mine some ores and go back to the base to sell these ores. So again, in this case, we imagine a scenario with a nonlinear utility function where the miner, the agent, has a contract on which he can sell the ores at the preferred price. The leftover ores are sold at market price. There is fuel is taken into account too, and there is a penalty if the contract cannot be fulfilled, if the amount of ores is not enough. Okay, so we don't use the single objective time step variant as baseline, since we have seen in the previous experiments that it is not learning for nonlinear utility function. However, we are keeping the single objective baseline with the terminal rewards, since this one receives the correct utility. And we see again that although they're all learning, our algorithm learns well the fastest. It reaches the highest utility. And this is because it is able to learn at every few time steps. It is not need to wait at the end of the episode in order to make an update, as reinforce needs to do, and it does not have to cope with sparse reward signals, which is what the green line, the single objective variant, has to do, which explains why it learns faster. And it's a second experiment we did is exactly the same, except that we use a pixel variant of the environment, where we take the frames as inputs, we pass them to a convolutional net similar to the Atari games, and then we use the same utility function. Again, our algorithm is reaching the highest utility, while in this case the other ones are not. So the single objective one learns but is unstable, and more reinforced is not able to learn correctly. So this concludes our talk. So we have proposed a multi-objective actor-critic algorithm that is able to cope with non-linear utility function in the expected scalarized return. To the best of our knowledge, this is the first reinforcement learning algorithm that's able to do so. It is sample efficient and stable. And in future work, we aim to learn the nonlinear utility function by interacting with the user.